So, basically, this is a new series where I will be covering the 68,000. Of course, I will talk about the Amiga, but the main topic is the 68K CPU or family of CPUs. Most of the information.
Mamma mia.
Oh, thanks, JJ Barnum, for the subscription for months. Thank you. Hello, Tron. So, most of the information that I have, of course, comes from the book of Randy, but it was scattered, okay, of Fabio. But I also got my own, plus I did a lot of research, and I have from other sources too. So the information is not, it's collection of lots of things from different places. Let's put it this way, which I will name from where they came from. Well, some of them, others, if I found it in a forum, it's not something that I'm going to mention. Somebody writes some sentence somewhere, but yeah, it's all information. I didn't invent this information. Things that I found on the internet. So, as always, I start with the usual thing, but before I do that, I need to switch here. So, there you go. By the way, once I start the thing, once I start talking, there are two things. One, I cannot, for some reason, PowerPoint has his ways of selecting screens. I cannot find where to force it to go to one screen. So things might not be so elegant initially till I correct them. And secondly, and this is a test or a trial, after my, say, talking, there will be, I will show a demo or two, and at the same time you'll have to answer some questions. There's a quiz. So yeah, let's see who the winner is going to be and how much you pay attention. So let's start with the usual ritual. Please like and subscribe to the Phase 101 YouTube page. Remember that under each video there are links for sources related to that video most of the time, and the link to the sources goes to Mega. Okay, I do not like to use GitHub for a reason, because I want the source for that stream to be separate. If I had to use GitHub, what will happen is all the source will be in one place, and people has to revert back to find for that episode. So I prefer to have all the source related to that episode in one place. So that's why I prefer Mega, and I do not use GitHub. Like that, you can download the source for that video and you can exactly follow. Of course, my Facebook page and subscribe to my Facebook Phase 101 group if you want to follow us. And I have the other group, Commodore Dev, where everything related to Commodore goes there. If you write to me on Facebook, I will reply, but I take time. On my Discord, then I will reply normally very fast. And if you are like Docster messaging me all the time. You know that I reply very fast. Besides Discord, I have a Telegram group if you want to join. If you don't like Facebook or Discord. I mean, this group, this is growing, but very slowly compared to Discord, okay? So I do not expect miracles on it. But people do prefer it. There are people that do not like Discord, do not like Facebook. So anyway, if you want to support us and go that extra mile, then you can either support us using Patreon or Ko-fi. Both of them has got the same thing. There are no difference between them, and if you do so, you unlock 88 videos, which are not available on YouTube. And this should grow even more this month, given that I get time. That's basically it, and we can go to the main screen. So, where is my main screen? There you go. Before I start, I like to, you see the logo on this side of Retro Passion. I'd like to thank him for taking care of my Amigas and fixing them and doing all this stuff that you know, that they needed. Also, he managed to he fixed two before I went to Malta in November, and he was very quick in repairing them and sending them to me and doing all this stuff. And he was very how to say, professional, in the sense he gave me the details of what was really wrong with them. So I could understand better what to do and whether I should fix them or not, for example. Because, for example, my A120 needed more attention than I thought. But now he has another board. He has another Amiga 1200 of a friend of mine, to be honest, which he's taking care of. So I really like to thank him, because also he will, I know that he will do it in a, in a quick, or when I need it. I know he will send it fast. If I tell him I need it by next week, not next week, by the end of the month, I know he will do it by the end of the month. So yeah, thank you very much, Retro Passion, for all the help that you have provided me. Now, before I start and show the title, why it is called, Learning Amiga 68K, Amiga 68000 Assembly with Docster. To be honest, when I started this, there was no Docster, okay? But then Docster came up with the idea, or the same idea that I had in a way, but he also started producing things without me asking him. And he sent me lots of code so that I share with you guys. Hence, why with Docster? Because he went so deeply into it, trying to learn the instructions, that he even provided me with examples of what he was trying. So, yeah, that's why with Docster. You will see at the bottom in the left bottom corner that initially my slides were not called learning Amiga 68K assembly with Docster. So this is how it came to be, how I have Docster in the title, because with all the respect, he deserves it. He really did well. So now, given that I click and I don't have any issues, there you go. That's the title. The for beginners, I left it, but to be honest, it is learning Amiga 68000 assembly with Docster. Okay, the beginners are just to show that is that it is. I mean, this is for beginners. The slides, I only have few slides. There are about 40 slides, if I'm not mistaken. But after these slides, I will not continue to use PowerPoint, okay? It's just the beginning. Hello, Gary. I have to say, this series, I started it in writing it 1 month before the book finished. And the book for this is about 200 pages right now, roughly, okay? It was 160 in December, but now I think it's about 200. It's not really a book. It's a series of notes all together. Let's put it this way. So I try to cover things that beginners want to understand or need to understand so that they can start coding for the Amiga, because, you know, the book immediately started you on the Amiga. And although Fabio did explain the instructions as he went along, but if you needed to look at the instructions, there wasn't a way. So, because you needed to find, okay, he talked about compare maybe in chapter 3, but then he talked about, I don't know, move in chapter 2. So they were all scattered. And here I'm trying to collide them all together. Now, the second sentence is building blocks, and that's why you see these towels. It's a building block to bare metal coding, because programming the CPU, okay, is bare metal, okay? Now, calling system calls, that is not bare metal coding, but everything that we do here is going to be bare metal. There are no system calls. And when I see modern assembly, okay, using they are saying assembly, but then they use system calls, I'm sorry, but that is not pure assembly for me, no matter what they say. Pure assembly is just the CPU and nothing else. And of course, the hardware components with the CPU. So I'm emphasizing on the bare metal just to make you aware there are no system calls in what we are going to do. Anyway, now here's the credits for most of the stuff that I have here. So some of the info is based on Fabio Cicci's book, okay? Because I gathered it from lots of places. Examples, when it comes to the instructions, this is Docster's work, most of it. Some info is based on the famous doc How to Code version 7. You can find it if you look it up. Some other info is random, you know, what you find in online on the internet. All diagrams in these slides are mine, except for 1 or 2, which was impossible for me to do. And they are related to the 68,000 per se. So Motorola owns them, let's say that. Okay, objectives. Of course, 68,000 CPU architecture, addressing modes, tools used and set up. This I will cover. I know Docster asked me this yesterday. I will show you how to set up an Amiga in WinUAE, and I want all my examples to run on WinUAE. Hello, school coder. So you'll set it up. I'll show you how to set it up, and I will tell you the tools. There is a need why you need WinUAE also. All the graphic tools, no matter what tool you use outside, on Windows or Linux, no matter what tool you use, in the end, you'll need the Amiga. Because to convert it and to have it in the right way, especially in the beginning to understand what's happening, you will need the Amiga. Of course, I'll cover the instruction sets. I will cover optimization. This is covered, and this is where I took big part from Fabio's book, where he talks about optimization, but I also have from others that I found. And of course, I'll try to cover also the other CPU families of the 68,000. So, as I said, there's a quiz at the end of this stream, which I will be playing a demo and you will be doing the quiz. For once, I can watch the demo and let others, how to say it, to scratch their head, because normally I do not watch the demos, others watch the demos and I am doing something else. Okay, so let's start with the 68,000. Now, some of you know lots of things about the 68,000 because they have done 6502. But there are things that will catch you on the 68,000 because you are used to 8-bit. However, the advantage of having done 6502 is huge compared to somebody that didn't do anything, because the 68,000 have many instructions that are similar, except for load accumulator and store accumulator. Those, you have to forget them. So, history. The CPU was introduced in 1979. It is called 68,000 because it has 68,000 transistors, for those that do not know. It was used in the Sun Workstation, Commodore Amiga, Sega Mega Drive, many more. And of course, the family is the 68010, 68020, 68030, 4060. Okay, this table is important, okay? You tell me, oh, I'm going just to program for the 68,000. Yes, you're going to program for the 68,000, but if you run it on an Amiga 1200, which has got a 68020, it has the other stuff. So you need to be careful when you code and you want the code to run on both machines. So this is why you need to know these bits. So if you notice, the 68,000 data bus is 16-bit. All the others are 32-bit. The address bus of the 68,000 is 24-bit. All the others is 32-bit. So the Amiga 1200 is fully 32-bit. Imagine that when Windows was out. Okay, to become 32-bit, Windows took ages after the Amiga 1200, while the Amiga 1200 was already 32-bit. Data cache. From the 68030 onwards, the CPU has data cache, okay? And you can see the various sizes. Now, this one is important. Instruction cache. The 68020 has got an instruction cache, okay? Hence, why it is also faster, because it can read, let's say, or remember instructions that it read. So when you are in a loop, it can remember and execute those instructions more quicker, because they are in its own RAM, let's say that. The 68030 has got a memory management unit and the rest, and all the CPUs that follow. And an FPU is available from the 68020 onwards, but from the 68040 it's also on chip, so it's on the CPU. So for example, my Amiga 1200, one of them has got an FPU. Okay, I installed it on the motherboard. Actually, RetroPassion installed it for me. So I can use it with a 68020 and an FPU, and I can use it, actually I have also a 68030 and with the FPU. So it has those modes. It's very, trust me, you will need to remember this table. What is special about the 68000? Powerful and simple instruction set. It's very true. Able to support high-level languages. Good for operating systems. True, because of its interrupt system. Flat memory map. Compared to the segmented memory model of the Intel, this was a killer to the Intel machine back then. Internally, it is always 32-bit. Hence, 32-bit instructions. Externally, the data bus, as I said, is 16-bit. Hence, it is 16 32-bit. It's a 16 because internally it is 32, but externally it is 16. Since the data bus is 16-bit, then it is a 16-bit CPU, because CPUs are measured on the data bus, external data bus, not internal. However, from the 68020 and above, the data bus is always 32. Hence, they are all 32-bit CPUs. The image is from the Motorola handbook. I could not do that. So, 68000 specifications, 32-bit data, and address registers. The registers, internally, they are all 32-bit. 16-bit data bus for the 68000 and 24-bit address bus. Addressing modes 14. Some people do not agree with 14, but it depends how you look at it. Memory is mapped, so full memory range. You can access all memory without segments. You have a program counter, 56 instructions. Now, this, when you look at the instruction set of this 68000, you say, oh, it's 56 instructions. That's not true. It has a lot more, but the assembler hides most of them. And because they are all the same, move M and move A, the assembler treats them as move, and hence you just need to know move. The assembler will change the instruction whether you move to an address register, whether you move to the stack, so it knows when to change the instruction. And it has 7 levels of interrupts. not like the 6502 guys. To program the 68,000, well, what you need, remember, we said bare metal. To program the 68,000 CPU, one uses the CPU registers, of course, the instructions of the CPU, the memory that it comes with it, and you manipulate, let's say, devices or I/O by accessing the special registers that are available depending on your hardware. This is the second diagram that I have from the manual of the 68,000, but I did produce this, so you're going to see it in a minute. Just I made it here, it is all together, while in my version it's not. However, notice there are 8 data registers. I'm looking at the block to the left, the 0 to the 7. Each register can have 8, 16, or 32 data. And you can see here the range, 8, 16, 32. On the right side, we have 8 address registers. And they can have, there's the distinction between data and address. They can have 16 or 32. There is no 8. Okay, it's an address. It cannot be 8. You have the program counter, which for the 68,000 is 24-bit. And then you have the status register, which we know on the 6502, but it is not 8-bit, but 16-bit. And it's divided into two. One is the conditional code register, where the flags sit, and one is the status byte or system byte, whatever, is where the interrupts, supervisor mode, and trace mode are. One thing I need to tell you, A7, because you don't see it here anywhere. Where is the stack? Where is the stack pointer, which we are used in the 6502? Well, the 68,000 has it with the register A7. A7 is the stack pointer, okay? You can change that value if you want. You can manipulate it, but it is advised not to. Normally you crash the machine, unless you know what you are doing. So A7 has two names, either A7 as address register or as SP. If in the assembler you type SP, so stack pointer, is the same as typing A7. Basically here is what I just said. So data registers are from 0 to the 0 to the 7. There are 8 of them, and they are 32-bit. Address registers, there are from 80 to A6. Notice I skipped A7. So there are 7 actually available to you, not 8, unless you know what you're doing, let's say that. 32-bit, and also 16 and 32-bit. Notice that data registers are 8, 16, or 32. I should have that. That's a mistake. Not 31-bit, 32-bit. Okay, I need to correct that eventually. I'm going to take a note. So this is slide 12. Good one. Nobody spotted it. So stack pointer, that's why I left it out, is SP. It's a word, okay, or it can have two, and sorry, it can have two, and not a word, it can have two, and I will come to that. It is A7 or SP, as I said. Why it has two? It has two stacks because it can, the CPU can go in supervisor mode or user mode. Normally you are in user mode, but when you go in supervisor mode, you have another stack. The stack pointer is different. No. That is, but how much it can store? 32-bit it can store. No, not 31. But yeah, program counter, there is one 32-bit, contains the address of the next instruction. No. And status register, SR1 is 16-bit and contains the information of the on the result of last instruction. Okay, so for the flags, and consists of a system byte and the conditional code register, where the flags are. This is my humble representation, okay, of what happens in the arithmetic logic unit. The 68,000, most of the time, okay, so I took school coder. Yeah, you all fed. So normally you have source, which is on the left side, and destination, which is on the right side. The 8086 is opposite, okay? Source is on the right and destination is on the left. They have to do it the opposite, but because it's Intel. So you have two source and destination. When you do something with them, you set the flags. So one of those flags is set, and then you have a result, and the result is always stored into the destination address. Okay, I hope this makes sense. I mean, I try to represent it, I looked a lot about this, how to represent the ALU and how it works it out, and this is how I came up with it. The control/status register. So we're going to talk about the status register where there are the flags and the system. So it is 16-bit, as I said, divided into two. One is the system byte, which can only be modified or accessed in supervisor mode. And when I say access, it's with instructions. So you have to put the CPU in supervisor mode. Or the user byte, which is called the conditional code register, which that is always available. It's in, well, even in supervisor, which is the user mode, and it behaves depending on the instructions. This is where the flags live, no? And here is a better, I think you can see it better than the chart that I had before from the handbook of the 68,000, where I'm showing the status register divided into system byte and conditional code register or user byte, okay? And then you have the 5 flags, and notice there is one called X, which is called extended bit. I will tell you why there is an extended bit in the 68,000. There are 3 bits for interrupts, and then there is the S to go into supervisor mode and the T to go into trace mode. This is, debuggers use the trace mode normally. Here you'll see why I said about the extended bit. So C, you all know, it's the carry, okay, or the borrow. So depending on the result of an instruction. Well, those bits, I'm explaining 68,000. I'm not explaining 68040 or 60 or whatever. So some of those bits are used in other CPUs, but let's keep with the 68,000. Same for the instructions. The V, we all know it is the overflow. The Z is for the 0 flag. The N is for the negative flag. So far is 6502 exactly. Then there is the X. X is used for precision, okay? When you have addition, okay, subtraction, etc. It gives you that ability, retains the carry bit so that you can have more precision. And in the book, for those that followed, I covered some examples of that. Then we have the I, which is from 0 to 2. These are the interrupt. S is for the supervisor, and T is for the trace. So when you're doing debugging. This is where the 68,000 gets you when you move from 6502 to 68,000. When you are using an instruction in the 68,000, you need to tell it on how many bits that instruction is going to work. So you all know bit is the smallest amount, okay? And it can either be a 1 or a 0, basically. It also has like the 6502 binary coded decimal, which uses 4 bits, and it can give us from 0 to 9. These two, this binary coded decimal, you rarely use it. Let's put it this way. And bit is when you are testing. The 6502 doesn't have bit testing, but the 68,000 has a lot. However, these and then there is the nibble, which is the same as binary code but 4 bits. But the next 3, byte, word, and long, is what you need and what you need to specify most of the time. The default is always word. So if you don't specify it, the CPU will assume that you're trying to work on a word, so 2 bytes, okay? I recommend that you always specify the size, okay? So you can specify a size, which is a byte, you can specify a word, or you can specify a long word, which is 32-bit. Here is a better representation of what I said, where I showed the nibble, which is 4 bits, binary coded decimal, which is 1 byte, but for 2 nibbles, as you can see, so you have from 0 to 9, 0 to 9, then you have byte, you have word, which you have low byte and high byte. Okay, so it is 16 bits, yes. But you have the low byte and the high byte of a word, and then you have the long word, which you can say low word and high word. So long word is 32 bits, long word is the first 16 bits, and high word is the second 16 bits. But you can also specify byte 1, byte 2 of a long word. No, it's not normally used, okay? But you can say byte 1 of a long word, or byte 2, whatever. This, you should know it all, okay? Bits, nibbles, bytes, words, and long words. So a bit is a single binary digit, 0 or 1. Some of these are repetition, I know, but it's the context. You have to understand that I'm changing context. A nibble is 4 binary digits, or half a byte. A byte is 8 bits. A word is 16 bits, or 2 bytes. A long word is 32 bits, or 2 words, or 4 bytes. This is where it will get you, okay? The word, long word, byte, word, and long word, okay? it will get you here, the 68,000. I don't know how many times I had bugs because of this. Because you specify, you think you're working on word, and actually, or working on long word, but you're actually working on word, and things like this. And then there is the quad word, which is 64 bits, or 4 words, or 8 bytes. So it's double the long word, the quad word. You know this also, the units, kilobyte, megabyte, gigabyte, and terabyte. You know them from the hard drives most of the time. Kilobyte is in 1024, megabyte is 1 million, gigabyte is over 1 billion, terabyte is over 1 trillion, and after terabyte, what is next? Pico, no? Picobyte. I didn't mention it there, but yeah. Yeah. So, permutations, of course, this is to explain it to kids in a way. So I use the bulb effect. So a bulb can be either on or off. So that's a bit. If you have two bulbs, then you have 4 possibilities of on and off. And here are all the possibilities with from having one bulb, to four bulbs, and each bulb is a bit. Okay, so you know all this. So decimal and binary systems. So we always think in decimal numbers now, from 0 to 9. Thinking of how computers store information requires knowledge of the binary base 2 number system. So computers, I'm going to continue from the middle. Computers can only understand 0 and 1. There are other number systems you need to know besides the binary and decimal system. The numbers, okay, the modern numbers that we write, modern numbers, well, the decimal system, okay, the numbers are positional. So the 2 is 10 to the power of 0. The 9, if you look at the example that I have, the 9 is 10 to the power of 1. And it continues like this, as per table that I have under it. So 8192 is, the 2 is 10 to the power of 0, the 9 is 10 to the power of 1, the 1 is 10 to the power of 2, and the 8 is 10 to the power of 3. So you get these numbers when you do that, and if you add them all together, you get 8192, as per my example. So the decimal number system is known as base 10. The value of the position are calculated by taking 10 to some power, power n. It is called base 10 because we use 10 digits starting from 0 to 9. The binary system works on the same principle, but the binary system can only have what we said before, bits. So we can only have 1 or 0, and it's the same thing. Because it's a 2-base system, then it's 2 to the power of 0, 2 to the power of 1, power of 2, and power of 3, as you can see on my table. The numbers that you get, so it's also positional, okay? It's 8, in this case 0, 0, and 1. If you add them together, it's 9. So 1001 is 9. It is known as base 2, as I said. The values of the positions are calculated the same like decimal, 2 to the power of n. It is called base 2 because we use 2 digits starting also from 0 or 1. So this is like 27. So binary to decimal, to convert binary to decimal, if we have 8 ones, okay, as you see in the example, then we will need to use the same system. So starting from left, okay, we have 2 to the power of 0, 2 to the power of 1, and we continue till 2 to the power of 7. So because we have 8, okay, of them, so from 0 to 7, you add all those together and we get 255. I mean, guys, you know this, but remember, it needs to be done for others. Oops. The symbol for binary numbers is percent. I'm mentioning the percent number because this is not 6502 also use percent. 68,000 uses percent, but not 8086. Okay, so I'm mentioning it to make it clear that it's not a standard in all CPUs, but in Motorola or most CPUs, they are the same. Converting decimal to binary is by, if you look at the example that we have here in my table, we have 103, and the value of a binary would be this. To do it, you start by dividing, let's say 1 to 8 in this case, okay, sorry, subtracting the value from it cannot, basically 103, 1 to 8 is bigger, so it cannot fit, so it's a 0. Then it fits, okay, so we put a 1 and the remainder is 39. Then we have 32, it fits, so we put a 1 and the remainder is 7. 16, it doesn't fit, so we put 0 and the remainder is still 7. 8 is still 0 and the remainder is still 7. Then it continues like this. 4, you have 1, so we put a 1 because it fits, and remainder is 3. 2, yes, it fits, so you put a 1 and we have 1, and then remaining is 1, which is 1 basically, and the remainder is 0. So that's when we end. Anyway, so that's converting from decimal to binary. Working with large numbers. Humans can't really read binary numbers. They are too many digits to deal with. Memory addresses and other types of data can be quite large. You can see that 32-bit is quite a large number if you had to use binary. Hence, we use hex. So, the hexadecimal number system is base 16. The values of the position are calculated by taking 16 to some power n, okay, to the power of n. It is called base 16 because we use 16 digits. So the normal ones, 0 to 9, and then A to F. So A is 10, B is 11, C is 12, D is 13, E is 14, F is 15. The symbol used for hexadecimal notation number system is the $sign. Again, I'm mentioning it because in 6502 and 68,000 it is the same, but not in 8086. Just to mention a CPU, and since there is Dr. Honey here. So here is a table which you all know: the binary value, the decimal value, and the hexadecimal value. Okay, so F is all ones in binary and it is 15. We know this table by heart, no? The numbers in the hexadecimal system are positional, same like previously. So if we have 7 FFD, sorry, if we have 32765, which is 7 FFD. Anyway, so it's the same thing. You take the 16 to the power of 0, 1, 2, or 3. We have 4096. Okay, so in 4096 we managed to fit 7. Okay, if we divide 32765 by 4096, then what remains, we which is 16 to the power of 2 is 256. We managed to fit F, and it continues like that. So we end up with the number 7 FFD. Yes, but I didn't want to use that number, and this is why I got confused. I mean, I questioned myself right now, because I remember when I was doing it, I said I do not want to use 8000 because that is too easy. Converting hex to decimal, so now we take the opposite. Okay, so we do 7 times 4096, which is the 28,000, 28672. Then we take the F times 256, which is 3840, and we continue like that. When you add them together, it is 32765 again. So the opposite way around. Hex works well with binary, taking back the binary long number of whatever. We can take this, we can make it more readable by doing the grouping of the nibbles, because with a nibble we can represent from 0 to F. Okay, so if we group them, we end up with 50A7. So that's more readable for us, no? So memory addressing. Now this, I'm mentioning it, most of you will forget it. Okay, you will forget it because you'll encounter this at a later stage, but it's one of the many times when you will get a guru. Okay, that's a quote actually, Hound Dog. You can add it to the quotes. So word addressing, when you are addressing memory, so address registers. Okay, when you are addressing memory, you use the address registers. The word needs to be aligned, what is called alignment. So an address can never be at an odd address. It always has to be even. Because of that, we have an instruction in the assembler, no, sorry, directive in the assembler called even. We actually also have another one called CNOP 0,2. It means align to the next even address. So notice the image that I have to the right. Okay, an address, I mean word aligned, okay, is from 0 to 16-bit. Okay, so 16 bits is 2 bytes. Notice that if we start from 0, the next one is at 2, then at 4, then at 8. It cannot be 1. Okay, So the alignment is always every 2 bytes. Attempt to store, okay, an address or use an address which is odd, you'll get the guru. What old school coder said, you will all become gurus. And it will get you guys. It will get you, and you will be swearing at it a lot. This, okay? Now, from the 68020 onwards, this was fixed. The CPU is able to read at odd addresses, but it reduces its performance because of this. So always avoid odd addresses. Now, this is what I'm going to say now is hard to imagine yet. Long word addressing. So same like we have word, it needs to be at an even address.
Mamma mia.
Oh, Docster. Oh my god.
Mamma mia.
And you triggered it again.
Mamma mia. Mamma mia.
You triggered
Mamma mia.
You triggered it again, Docster.
Mamma mia.
Okay, so thank you, Docster.
Mamma mia.
Thanks, Tron, for the follow. I will sort out the issue of the numbering. Thank you for giving the 5 subs, Docster. You're always, I mean, like old school coder says to you, I mean, thank you. I mean, I do not know what to say sometimes, but you know, I appreciate, and you do not need to. I mean, for me, being here is, you know, is what really counts, and what I really appreciate. Somebody hearing me,
Mamma mia.
you know. Thanks, Night Shift, for the follow. So thank you for giving a sub to what is it? Which sub? Okay, to Conrad. Okay, to Lolo, to User Mayday, to Ilmeno. Ah, hello Ilmeno, and to Flopine. Yes, you gifted 135. I'm noticing it now, actually. Yeah. Wow. Yeah, I mean, I do not know what to say. Anyway, he wants the record. What can I... he wants the record. So, what I was saying, long word needs to be at an even address, same as word, okay, same as word addressing. But when you are coding on an A1200 and using the AGA graphics, sometimes you need to align it not to even address only. It has to be divisible by 4, the address. Okay, so if we start from 0, 4, 8, 12, 16, etc., the CPU, the graphics will work better, let's say that, if you align into that mode, because it has something which is called burst mode, which I will not go into it. But it's one of the reasons why you need to know this. So it's not only even, it can also be aligned to a number, to an address, divisible by 4, not just by 2. Hence, we have two directives. One is even, to align it to the next even address, or CNOP02, but to align it to every 4 bytes, every 4 bytes, let's say that, or a number divisible by 4, we have CNOP 0,4. Again, an attempt to store or to access a long word using an odd address will give you the mighty guru. Okay? Long words, remember, are 4 bytes or 2 words. And I believe, no, but I'm close to the end, I know. Odd addressing. From the CPU 68020 onwards, okay, it is possible to use odd addressing, I mentioned this, but the CPU suffer performance. Therefore, it is still recommended to avoid odd addressing. And that's the end of the slide. So if you have questions, please ask. I will be streaming tomorrow before Old School Coder, just doing the book. Now, there are lots of books about the 68,000. Let me find it. This is the most famous. Oh, let's see. But it's very hard to find, and it's very expensive when you find it. I don't know if you can see it. Anyway, you can see the book. However, try to find this book. There we go. Now, this book, I'm going to tell you a small story about it. I got this book by, let's say, accident about 2 years ago. And I was still living in Cambridge when I got this book. Now, this is written by an English professor that teaches at the University of Middlesbrough. And it's a very good book. I think you can still see it, no? It's just the title that you need. Yeah, the thing is trying to eliminate the book because it has white. That's what I did. Okay, so guys, try to get this book. And what I like about this book is that it also has questions and answers at the end of each chapter. And it comes with a floppy. I mean, the floppy is not important, but there's an emulator that you can run on DOS, okay? On a DOS machine, now on Windows, whatever, that emulates the 68,000. It covers only till the 68020, okay? It doesn't go above the 68020. But it's a lot cheaper, this book, than the other one. And although I like the other book, don't get me wrong. Well, I have the original, not here, but I do have the original also. And I had that because somebody threw it away. And this was at work a long time ago. And I took it. But yeah, try, if you don't, because this one, as I said, this one is quite difficult to find and very expensive normally. But this one I found very good. So yeah, go for it. It's a very good one. Okay. Thank you very much for being here, for trying my test. I hope you liked what I did. It took me some time to start this series, but I hope I you like the series basically, and yeah, we continue from there. So thank you very much, and see you, most of you, tomorrow, no? On Oscar Coder stream, or maybe on my stream, and then you go to Oscar Coder, no? So that we can rate him. Thank you. Bye bye.